So first of all, I'd like to thank the organizers for organizing this meeting. And for me, this is actually so I would say Margit and Margit Rüssler, Patrice Sawyer, Piotr Grzyk and Jean-Philippe Anker. Thank you very much. It's very nice to be again at Lumini. So actually, on the way in, I thought, well, when was it the first time? And actually, I realized that it was 30 years ago. So it's a kind of 30th anniversary. 30 years ago, I was here for the European School in Group Theory, while still a PhD student. So it was really nice to be back. This is then completely new for me. And I should say that since this is actually my first kind of almost post-corona meeting, I decided to do this talk on the blackboard because I've been in so many Zoom meetings with PDFs. At some point it really bores you. So I thought we should at least try to use the fact that we all came here, some with considerable effort, so that we could have some interaction. So please don't hesitate to interrupt or ask questions, or hopefully I can answer them. And then let's see how things go. And that's also why I decided to do it on the blackboard. This is one of the reasons, the other reason being just lack of time. So I'm not supposed to use this blackboard. So that will do only for the people here, right? Okay. So to start off, let me say that this is based on a recent preprint with G. Lou. She is a PhD student in Radboud University, so where I am located. And the supervision is also done with by Maarten van Pruisen. Some of you know him very well. So what is my general goal? The general goal is to understand matrix spherical functions. This actually goes back already a long time, since even the first papers on spherical functions, like the ones by Godemand, for instance, in the 50s. And so the idea is that we want to understand them in more detail and try to understand them in more structural way. So many people already worked on it, and so what we really would like to understand is really how are they related to orthogonal polynomials, matrix orthogonal polynomials. So these polynomials, matrix orthogonal polynomials in one variable, were already introduced from a completely different point of view in the 50s by Krein. So he studied them in relation to differential operators and spectral theory. And then later on, it turned out that they also occur on rank 1 symmetric spaces. Let's say that maybe the first instance is the one by Kornwinder in the 1985, I think. And then later on, also by Grünbaum, Paccheroni, and Tirao. And so this was the motivation to look at the more higher rank cases. And so what I want to report on is a higher rank case, which is only rank 2. Although many of the things that I'm going to discuss, we know how to do this in arbitrary rank for this particular case, so the BCN type. But only in rank 2 we can fill in all the spots. So I'll mainly stick to the rank 2 case. Okay, and of course in the end, in the future we want to extend this. We would like also to do the quantum analog of this, but this is still, of course, well, in the future. So I will, so let me write down. So this is joint work with Jie. From now on, G will be SUN plus M, and K will be the S of UN times UM. So this is a very well-known symmetric pair. And I must say that almost all of what I'm saying is in the case n equals 2. And of course, m is bigger than n. So this is the setup, but a lot of things actually hold true for more general symmetric pairs. I should keep an eye on the time as well. This is our setup. So what is it that we want to do? Well, we want to take a representation, say mu is the highest weight for k, and we have the corresponding representation. I'll try to be labeling the representations for which groups. Typically it's K or G, but I'm trying to be precise here. So there is some fixed representation here. And what I want to look at initially is I want to look at this space of linear maps of this representation space. Of course, it has to be an irreducible representation, right? So it's finite dimensional because we were completely in the compact setting, and I'm interested in this space, and this space. So this space has a k times k action, right? Because you can multiply from the left by the action of k1, and you can multiply by the right, on the right by the action, say, of k2, but then, of course, take its inverse. So this has a k times k action, and we also have, say, the space of regular functions on G, and this has a G times G action. And so we have two of these spaces, and of course, if it has a G times G action, I can also restrict to k times k, and I'm looking at the tensor product of these two representations, but now I consider them as k times k representations because, well, k is a subgroup of this one. So I look at this one, and from that representation, I look at the invariance. So that is the space that we are trying to understand. And so this space, of course, depends on the representation mu. So denote this by E of mu. So that is the space that we would like to understand in more detail. Right. So then you, of course, can think of this space. You can think of this as so what we do is we think of this as functions on G that end up in this space. And what does this invariance mean? That invariance means that if I take, so if you work out what it means, then you get that this function phi, so capital phi is an element of E mu. If it has this transformation behavior for all the k's in K, and for all the g's in G. So that is the transformation behavior that is imposed by the fact that we want this to be invariant under the k times k action. So that is the space, and of course, if you realize that if you take mu to be the trivial representation, then these are just the bi k invariant functions, and that corresponds to this one being, well, we know that this is a Gelfand pair. Okay. Right. So if we want to understand this space E mu, so then we see that E mu, well, since this is an algebra, so you can multiply two of these functions and it's still okay. But we also see that E mu is an algebra over if 0 denotes the trivial representation, because these are just the bi k invariant functions. Right, and so nu is that's the trivial. So actually what we would like to understand even more is how is this algebra related? How is this an algebra over the space of bi k invariant functions? Okay. Right, so that is, you see that this is not specific to these cases. You can do this for general setting. So let me make the first assumption that we have to make a few assumptions on the way. So what we'll assume is that, well, I just said that if you take mu equals 0, we know that this is a Gelfand pair, and so we assume this is also true for arbitrary, for such a specific mu, right? So we fix mu, so this one is really fixed. So that this is multiplicity free. So meaning that the induced representation, that it splits multiplicity free. So that's our assumption. And so that means that if I take any highest weight representation of G, restricted to K, it will have this representation at most once. And let's also introduce some notation. So the representation of, so the highest weight representations for highest weight lambda of G, for which this multiplicity is actually 1. We denote this by this P plus of G at mu, so these are the lambda, let's say G hat, highest weight of G, such that this multiplicity is actually 1. Right, so that these are the lambdas that, upon restriction to K, do contain this irreducible representation. So, of course, then, so we know that if I take the trivial representation, these are just the spherical weights. And if we stick to our case here, as n plus m, and if I take n equals 2, then we know that this is, in this case, is just, well, this is just generated by 2 spherical weights, and this is in the paper by Kramer from the 70s. So we know exactly what lambda 1 and lambda 2 is, and we also know this in the general case. Okay, so now if we now take a lambda in this set, so then we know that there is a K intertwiner, and I'll denote it, let's say that it's J, so this is the K intertwiner. To this representation space for G. And of course, we assume that all representations are of course unitary, and this J should also be unitary, so it's unique up to a phase factor. And so now we can define, say, phi depending on mu, of course, also depending on this lambda of G, and we'll just define it by, well, you start with J, you go from Vk mu into Vj lambda, there you act by the G representation, and then you project back. And so this is a map that ends up in this space. And this one obviously has the right transformation behavior because J is a K intertwiner. So we have all these functions, and we would like to understand these functions better. Of course, you have to understand what is P plus G mu, what this set is, how it looks like, and understand what is going on. So maybe I should write that down here. So this V mu lambda, this will be in this space, E mu. Okay, so let's maybe write down a few facts. Well, first of all, these so this spans, and is actually a basis for these E mu. So you get all of them in this way. That's essentially the Peter-Weyl theorem. What's also nice is they satisfy, of course, orthogonality, since we, so this is span, orthogonality. Well, so if I take, here there's always a choice to be made. Let me make the choice by taking the adjoint on the right-hand side, but it's not essential. So if I take phi mu of lambda of g, so I end up in, so this is a linear map from vk mu into itself. This one is also a linear map of vk mu into itself. We assume the unitarity, so there's a natural adjoint. I take the adjoint of this operator and compose it with this one. I'll take its trace, and I integrate over g with respect to the higher measure. Then this is the dimension of vk mu squared over the dimension of vg lambda times the delta of lambda and lambda prime. And of course here lambda, of course here I take lambda and lambda prime in this set, because otherwise this function is not there. So this is just the Schur type orthogonality. And what is maybe important to observe is that this function here is actually bi-k invariant. And that's why you need this adjoint here. Because if I take, so if I replace, we have color chalk, so let me try this. So this is, I always have to convince the people at my university somehow that we still want boards that you can actually write on instead of just all these whiteboards and things that you can project on. And of course the best thing to happen is that if the higher technology breaks down, then you still have this technology. So this is really established technology. So let me use this even for this one. So if you put a k here, right, so what does it mean? Well, with the transformation behavior here, you get the action of k comes out here. This one goes out here as well. But since you take the adjoint, this one moves actually to this one, and then using the fact that it's a unitary representation, it cancels. Right, so it's right k invariant. Now I'm going to use the other color. And if I put it here, then this one goes out here. If I put it here, then this one goes out here, but because of the adjoint, it goes this out here. But it's a trace. Okay, so you can move this one over here, and then again it cancels. So this is a bi-k invariant function, and of course you can use all these formulas that you have for integrating bi-k invariant functions, so you can reduce this integral over to an integral over a. Right, so we are interested in integrals over a, so we can also restrict. Right, so we will have some k decomposition, and for this one, of course, you can easily write it down very explicitly. And this k decomposition means that we can restrict. So it suffices to understand this function restricted to a, and of course there are more properties. But if you do it, if you restrict it to a, then you actually end up in the intertwiners of this space that preserve the action of M, and that M, I should say that M is the centralizer of A in K, and of course this is also not very difficult, because if you are in the centralizer and A is in A and M is in M, then this one you can write as, because M is also in K, so this is also, and since M is in K, this is also the same as pi K. So it's this one. So we actually end up knowing, we only have to know it restricted to A, and then it's a relatively simple algebra, or relatively simple algebra. Because what we're then interested in is, of course, how this splits as an M representation. Let's say of certain highest weights. And that decomposition is then also always multiplicity free. So this is also going to be multiplicity free. And actually in our case, so let's just, right, so in our case that n equals 2, these are actually all one-dimensional. So they completely split multiplicity free, but also into characters. So these will all, so in this case, n equals 2, these will be actually one-dimensional representations. Okay, so that about the general stuff. Any questions here? It's maybe too elementary, but I like it. And since we have plenty of time, why not? Okay, so I should ask any questions from abroad? No? Okay, then there's maybe an important point here to make as well that, as before, if you take let me denote omega to be the Casimir operator, then there is still the radial part that you can calculate, although it's a bit of work. So this is now going to be an operator that acts on matrix valued functions, but you can actually calculate it. It's it's a bit of work, but you can do it. And then if you let this operator act on such a function, then you get, so this is restricted to A, of course, and this is just, so that is this C lambda, and this C lambda is the standard eigenvalue for the Casimir. Where, of course, this is the inner product you have to take on the dominant weights, on the weights. So this is also what we have. And this, most of it here holds in the general setting. Okay? Any questions so far? So now I'm going to erase the first blackboard. And I guess I have to use this one. Maybe I should say that if you do this for this case and, oops, and you look in the literature, then of course you have the Heckman-Opdam polynomials. So if you look at the case mu equals 0, so the trivial case, then this would be a special case of Heckman-Opdam for the case BC2 in our example, for the parameters that correspond to the dimension of the root spaces. And you probably also know that Kornwinde preceded Heckman-Opdam in the 70s with two rank 2 cases that he worked out. Well, actually he worked out more cases, but especially the A2 and also the BC2 case. So in a sense, what I'm going to show you at the end is something that is kind of a matrix analog of Kornwinde's BC2 case, or Heckman-Opdam's BC2 case, except in BC2 you have 3 parameters and we can only sneak in 2. Okay, so that's still an open problem for the end. Okay, now this seems to be almost dry, so let me write down the next assumption. So I'll now next assume a little bit about what the structure is of this space of representations that contain mu upon restriction to k, and I assume that it's of this form. So I'll assume that there is a finite set So this should be a finite set, let's say nu1 up to nu n. And actually I want this n to be the same n as the number of m representations in this restriction to k. So I want this n to be the same as that one. So at least why should something like this be true? Well, I told you in the beginning that this E mu is an algebra over E0, the bi k invariant elements. And if you have a pi g lambda and you tensor it with a spherical representation, and you look at the corresponding embedding, and you take the embedding then, and you take in the tensor product, you take a k fixed vector, then this will still work. So it will still have to give you a function of that type. So you can expect that adding a spherical weight, that you should remain within this space, right? So, and we assume a little bit more, namely that there is a kind of basic set or bottom set, such that all this space is actually spanned by a certain number of elements plus spherical directions. So this is what we assume, and the assumption is then also that the number of elements here is the same as the number of elements in this M decomposition of the K representation with highest weight mu restricted to M. Okay? So you can rephrase this if you take the tori in a reasonable way. So if you take the torus of M contained in the torus of K, essentially it means that the restriction to the torus of M of this one should give you an isomorphism from B mu into the set of M types that occur there. So that's another assumption. And of course, this is going to be slightly more difficult because how to describe this. So let me write that down here as well. So there is a preprint by Pezzini and Van Pruisen that actually give you the possibility to calculate all these. Well, all, but well, way too many for my what I need. So they give a calculation to all these sets. So they give a way to calculate. So they introduce something that's called the extended weight monoid. It uses a lot of algebraic geometry about spherical varieties. So you can ask questions. I would not know the answer. But this is, there's an explicit way to calculate this. It's a long paper, but it has a couple of tables. And so you can actually use these tables to read off what you want to read off. And then it's mainly just a minor combinatorial exercise to get this thing out, and then you can check whether or not this is satisfied or not. Sorry? Oh, way more general. So for all symmetric, compact symmetric spaces, but also non-symmetric spaces. Yeah. So it has a huge list, and so I think the table goes on for 2 pages or so, and we pick one tiny example out of it. So maybe this is also an advertisement for this paper. I think it's a very nice result. Okay, so let me now, let's now try to understand this example in slightly more detail and focus on a very specific case. Let me see where, okay, so here. So let's now fix mu. So how do we fix mu? Well, okay, I erased this blackboard. I actually looked at this advertisement picture for the sim, and then they had huge blackboards, like 6 in a row, and I was hoping that we could use these, so unfortunately not. So on this blackboard, I had this K in here. So what you can think of is U2 contained in K. And so actually what we do is we look at representations of U2 in here. So and now I take M to be 2, and M is bigger than 2, but of course the case M equals 2 you can also do. But then of course you don't get BC2 but C2. So what I do is we take a kind of a standard A-dimensional representation of this one, And then, of course, you can still tensor with the determinant. So I think of this as the mu and as A omega 1 plus B omega 2. And then, of course, you can still think of omega 1 and omega 2 as the standard weights of G, or the standard weights of K, because we take the torus of G to be the diagonal one, the torus of K also the diagonal one. So these omegas, they are just the standard weights. And so this dimension will be A plus 1. And from now on, I'll start numbering at 0 and end at A instead of going from 1 up to A. And if you then look at what's going on here, so in this special case, if you take that representation and you look at what M is, well, M is now going to be, so that is diagonal like this, something diagonal like this, and it's only this part that counts, and you see that it acts diagonally, so this one will now start from I equals 0 up to A, right? And these will be characters. And you only see these two elements there. Okay, so this is the case we would like to understand and get in a little bit more detail. Okay, now I already wrote down in this case that we know that P, well, this one we already wrote down. And in this case, this is lambda 1 and lambda 2 is this one. But this one, so this actually also comes out of the Pezzini-Van Pruijsen paper. But of course, this is already also in this tabella from Kramer's paper from the 70s. And so that's just one of the special cases in that paper. And now, for instance, let's take, if I now take mu to be omega 1, so I take the case A equals 1, B equals 0. So what you then do is you apply the machinery of Pezzini-Van Pruijsen. Yeah, so you know a priori already that this structure occurs. Then this is going to be, indeed, you can check that this is the case. And you can actually calculate B omega 1. And that is omega 1, but now considered as a G representation, which is kind of okay, because this is natural embedding of this U2 block into G. And the other one is omega 2 plus omega n plus 1. Now I need to check this because I never learned this by heart, but it's correct, this one. And so we know that this one, so this representation is two-dimensional, so think of it as the fundamental representation of U2. So this is an example. So this example also follows from Pezzini and Van Pruijsen, but the first case is already known for a long time. Still okay? Yeah. Okay. So let me write down a general statement here again. Let me call it a paper. So a theorem. This is actually in a paper that Van Pruijsen and Pablo Roman and I wrote, and that was published last year. And that says more or less some additional conditions. Let me not dwell on them. But they are not too, they are satisfied in this case. That even in the general setting you can, so if I now take this lambda of this particular type, so I'll write it as a mu I plus, let's say, a spherical weight. And this spherical weight, in this case, let me make it explicit for this case, is a d2 plus d1 lambda 1 plus d2 lambda 2, right? Where d1 and 2 are in n, so d is d1, d2. That's in n2. So that's the kind of general spherical functions. That you can always write this as expanded in these only in these new r's from this bottom elements, and that there are polynomials, and in this case in phi 1 and phi 2, And let me immediately do it from 0 up to A. So this is a new I. So you can expand any of these matrix spherical functions, right? So if we label this the new I plus a spherical weight, like in this way, then I can expand it in terms of these spherical functions that only occur for the news in this bottom. And then this one in front of it, so what is phi 1 and phi 2? These phi i's are the corresponding spherical functions for the representation with the spherical weight lambda I. And this is then a polynomial of a total degree, let's say, absolute value of d, which is d1 plus d2, in 2 variables. And in general, this also works in n variables. So now you see the matrix polynomials somehow pop up. Because what you do is you put these into a matrix because they are labeled. So these are the labelings of the matrices, and these are the polynomials. They are polynomials in phi 1 and phi 2. So in a sense, you want to understand these polynomials. And let me do it as I, in this special case, so I and R run from 0 up to A. So, okay, so then these are the polynomials, how they pop up. And so now you can ask all kinds of questions. So what is the orthogonality for this one? There should be, because they are orthogonal, right? What is a matrix PDE for which they are eigenfunctions? Well, they should also exist because the phi mu lambdas are eigenfunctions for a suitable Casimir operator, the radial part of it. And in general, how can we, well, what can we say more? Well, there's a lot to be said, and there's still kind of open stuff that goes on. So let me discuss this a little bit. I will try to discuss this in a bit of detail, and this is just a lot of complicated calculations, but essentially you can do this. Okay, so let me now erase this one, and then should I stop like 5 to 10 or?
If you do 5 to 10, then you'll have time for questions.
Okay, great. I forgot when the break is. Anyway, it's a lot of fun to have a talk on the blackboard. Of course, in general, if you want to calculate these polynomials, you need to calculate these spherical functions. And in order to calculate these spherical functions, you kind of have to get some control on these k equivariant embeddings that are used in order to create these functions. And this is something we cannot do very well. So somehow there seems to be a snatch there. And so the approach that we use in order to understand this, so instead of trying to calculate this k equivariant embedding J, for which we have hardly any control, we try to do it in a kind of approximative way. So we are going to approximate. And now the question is, of course, what does it mean? So I'll put it in quotes. And let me only do it for the elements in this bottom. My suitable, and I'll call these Qs. And the idea is, well, maybe I should recall A in this case. So let me take a generic element A of T, and T is, so now we are really back to this special case, T1, T2. So what is it? You can write it as cosine T1, cosine T2, identity, cosine T2, cosine T1, and then we put here I sine T1, I sine T2, I sine T2, I sine T1. So it's a very explicit element. So I only write it down to convince you that it is a very simple thing and you can actually do the calculations with this one. So this is our AT. So and this generates A. So this is, the identity is, so this is 2 by 2, 2 by 2, and this is then m minus 2 identity, right? So this is an identity of size m minus 2 by m minus 2. And what we want to do is we want to, these suitable elements here, so in terms, so you, okay, so let me put it differently. So you might also be tempted to do kind of approximation using the radial part of the Casimir operator and then see how things go, and then think of things like Harish-Chandra expansion, but that's, say, at the level of special functions and starting to work with the differential operator. Here we try to do this from the representation theoretic point of view. Now we have to, I want to do this a little bit better. And what I want these to all be homogeneous in cosine T1, cosine T2, and there are no signs. Oh yeah, I forgot to say something in the beginning. Of course, there is an action of the Weil group, and the Weil group acts on the M types. And the Weil group has two generators in this case, S1 and S2. S1 is a flip, and S2 is a sign change. And S2 acts trivially, so there are no sign changes, so they have to be polynomials in cosine T1 and T2. And so what we do is we replace, now let me immediately skip to, so first we replace phi 1, phi 2 by a suitable psi 1, psi 2, and these will be homogeneous. So psi 1 of AT will be cosine squared T1 plus cosine squared T2. And you can give them a representation theoretic flavor if you want. I'll not do this, but this is an affine transformation from these spherical functions to this psi 1 and psi 2. And let's now go to mu. So now I take mu equals omega 1. And what we do is we look at this tensor product. And then you can easily decompose this because, well, we know for G, this special SUN, that all these representations are realized in exterior powers. All these weights are then minuscule weights. It's easy to give some explicit abstract tensor product decompositions. And if you plug them in for this case, you get, well, of course, I don't know them by heart, but you get this one. And lo and behold, these two exactly give the B for omega 1. And what you can do is you can actually write down explicitly the K fixed, sorry, not the K fixed factor, but the K factor that is actually giving, let me write that down, V naught. So this is actually E1 wedge E2, right, because that's in this one, tensor, and then you take E1 wedge, and then you skip E2, and plus 2. So that's in this space. Now this factor, this is a K highest weight factor of weight exactly omega 1. Okay? It's a simple calculation. The only point is you need to find it. But that's there, and this is also a way to get these two, psi 1 and psi 2. Oh. Should not. Okay. So now let me then immediately go to the general case. So what is the general case? If I take a mu of this type, so and let's just for simplicity take B equals 0. The case B positive goes similarly. It's this one, so you apply the whole machinery of Van Pruijzen and Pezzini, and you can just write that out. It's this one, and then I skip the b equals 0, and so I runs from 0 up to a. So that's actually very explicit. So what we now do is we take a new I. I'll take a big representation. It's a big tensor product representation. So I'll now take this one, and I'll tensor it. I want to tensor it with this one, and that's that was a bit of a trial and error case because there are many candidates there. But in the end, we decided to put this one in, and that works. And that I take I times tensor. So this is a big tensor product representation. But of course, it has Vg nu I plus lower order terms if you decompose it. And then in this one, we take a vector. And this vector, well, we know that this was a representation for this G that is just a symmetric functions. And I'll take the highest weight function for that one. So that's in this part. And here I'll take this V naught, and I'll take it I times. And so let's call that U. Now the claim is that this U is a K highest weight vector of highest weight mu, which is in this case now A times omega 1, because I took B equals 0. But then I also know how to generate the K representation, because I just have to act by F1 repeatedly. So I get an embedding of the K representation with highest weight A omega 1 into this space. And what you need to show is that it still sees this space. And it does. So what you now do is you associate the corresponding function there. And now I really go very slowly. AT, so that is essentially the one that you get by embedding this, let me call it J prime, act by this representation that corresponds to this U nu IG, and project back again with this specific one. And now, let me now give this very briefly. So the point is that this one can be calculated explicitly in terms of Kraftwerk polynomials, which is not a surprise. And it's all homogeneous. And that Kraftwerk polynomials occur, that's not a big deal, because they always occur if you calculate matrix entries of U2 or SU2 representation. So that is very natural. And that can also be generalized to higher rank. But anyway, this is very explicit. And what we then can show is that, let me put it like this, a theorem, that the phi nu I is actually given by these Q nu R's, and that this is a lower triangular decomposition. So it's actually lower triangular. And that gives the following statement. So now, and these DRs can be calculated. And the calculation of these DRs is actually kind of that's really the step that one can check that is true. But where I don't understand why this is true of the same nature, and that is because it turns out that if you take the Casimir operator, the radial part, and act on this constructed elements, you get the right eigenvalue. So that's essentially okay. But there is one additional term, and nu I minus 1, with I squared for b equals 0. And this is kind of, so a priori, it will continue until nu 0. But apparently they don't occur. And well, it happens. But it would be great to understand what's going on. And let me then finally state what the orthogonality is for these polynomials. And then, I managed to go over time. So let me do that as at least that you can see how they pop up. And of course, you have to change coordinates in order to match it with the results by Kornwinder and the Heckman-Opdam case. So let me just say that there is an affine transformation of coordinates. Let me not worry about how they precisely pop up, but they do. It's not that difficult. So it's really, again, an affine change of transformation. So now I have to relabel these polynomials a little bit, so let me also call them differently. So this PD give rise to, let me call them differently, RD of x1 and x2, and we get this type of orthogonality. After reducing to A, and of course taking out certain symmetries, we get this integral, let me say, theorem, that we get an RD of x1, x2. Then there is a matrix, let me call it SA x1, x2. So this is an A plus 1 times A plus 1 matrix. That is essentially built up out of the Q nu i's. So it comes from this one, and it is a positive definite matrix. And you can actually calculate its determinant, no problem. And here I'll take the adjoint, and then I have a scalar part of the weight, and then I'll just write that down. Because we went through the labor of rewriting it in terms of Kornwinder's results from the 70s. Oh, so that should be x1 squared. And so this is 0 if d is not d prime. So it's a long formula, but essentially it says that this is the scalar weight of the Kornwinder polynomials, except that this should be a square root, except that in the Kornwinder case there is a gamma here, an additional parameter, but you get the m, which is a parameter, and the b. So now I plug in the b again, it's positive. So these two you get, but not the third one of Kornwinder. And I should also say that this is indeed a non-trivial orthogonality, because the commutant of this one is trivial. And also what they call the real commutant is also trivial. So it means that you cannot reduce it to smaller cases. So it's not a hidden scalar orthogonality. No, it's really an essential matrix orthogonality.
What is b, the exponent
B.
Yeah.
Yeah, that's the same b from. So I plugged it in again, just and I'll take it in. So for all the calculations, you don't need a b. So this one is independent of b. So the a only occurs in this part, and the b comes out as a scalar part. So essentially, this is just, if you look at Heckman's lecture notes for the European School group theory that I started with, which is in this book, then this is precisely the case that he does, I think, in chapter 5, where he looks at characters of a symmetric space. So that case is contained here. Okay, now let me not try to write down the matrix valued PDE for this one, but we can do it. And if you do this, this is a second order PDE because it arises from the Casimir. But if you look at the scalar part or the second order part, so the second order part is just kind of a scalar part, and that exactly coincides with the one that is in Kornwinder's paper from the 70s, and also Sprinkhuysen-Kuiper's paper. So the scalar part for the second order part is exactly the same. And then the difference is really in the first order part. And there all the matrices that occur are either diagonal, but not a multiple of the identity, or tridiagonal. And of course there's still a lot to do. I didn't discuss product formulas. I didn't discuss how to try to put this one in. So one of the natural ways to try to put this one in is by using shift operators. We haven't tried this.
But you get integer shifts.
You get integer shift, and then you need to continue,
Yes.
analytically continue in your parameters. So actually, this is we did this for rank 1 cases, and there you can still move around it, and I'm quite confident it will also work here, except that I don't know, so I'm guessing. So don't take this as a statement, it's my expectation. Okay, well, sorry, I went over time. Thank you.
We still have time for a few short questions.
Is that a classical Kraftschuk, one-dimensional or higher rank?
No, this is a classical one-dimensional.
Okay.
Yeah.
But it
Sorry.
it also occurs in higher rank settings.
Yes, I'm quite confident. Yeah. And these are the same ones that are, for instance, that are in Ilyev's paper. So that is the what was it? I forgot. Griffith's Kraftschuk analog that comes from statistics.
Mm-hmm.
Not yours. Of is it yours? No, I don't think so. No, it's not yours. Okay.
So you have a formula for when d is equal to d prime?
Yes. Yeah. So we have an explicit formula here, and essentially the only thing that you have to keep track is the original outcome of the sure orthogonality. So it will be a diagonal matrix which has these dimensions on the diagonal. And the dimensions will vary, but it will be diagonal. And of course, you also need to keep track of all, well, there's some Jacobians that you have to mess around, so there are powers of 2 and stuff like this. But you can keep it, yeah, you can make it explicit.
So that the diagonal entries have some reasonable product formula in terms of dimensions?
Yes, so you mean what comes out here at the right-hand side? Yes, yes, exactly. Yeah, so these are all dimensions, essentially dimensions of representations.
Any questions from the virtual participants? Any other questions here? Let's turn.
Oh, there's one, sorry.
If I understand well, you mentioned product formula in the last part of the talk.
Yeah, this is still open to do.
Can you develop it slightly?
Well,
what is conjecture?
Well, the problem is that we haven't had the time to look at it yet. But there is a general statement about product formulas for these matrix spherical functions. And that goes back to, I don't know, it goes back at least to the 70s by Tirao and so on. But it's not so clear exactly how to reduce it to something for the polynomials yet. But this is actually, this is just a matter of time, I would say, to see what comes out. But we haven't done it. So it's computationally quite a lot of work, and we just haven't done it yet. But I'm convinced that something should come up.
So let's thank the speaker again.
Thank you.